Hey everyone, my name is Jack and welcome to EECS 370 Discussion 8. Today we're going to be talking about the pipeline and data hazards associated with it. So in this discussion, we're going to give you a brief overview of data hazards and how we resolve them and how that impacts performance. So we have three main ways of resolving data hazards. We have avoidance, detect install, and data forwarding. So for avoidance, we insert no-ops into the assembly code. And then as you can imagine, since we're inserting no-ops into assembly code, this is more work for the programmer. Detect install. We insert no-ops at the hardware level. So if we detect that we have some kind of data hazard, we just stall the program and insert no-ops instead of fetching a new instruction. And then finally, we have data forwarding. So this is just a quick fix of some of the above to make sure we have less no-ops to insert. So let's get into it. So how do data hazards occur? So data hazards occur after we have a read after write dependency. So we can see in this example, add 123 has this register 3 is being read by NOR 345. And here we wrote to register 3 in the add instruction, but we read that register immediately after. And the problem occurs because we might be using the wrong data for register 3. And so these data hazards can occur up to 2 instructions away. So add 123, no op, nor 345. There's still going to be that data dependency. We don't get rid of it until we have 2 instructions in between. So let's say we had add 123, maybe LW 457 or something like that, and then no op, and then nor 345. This 3 is no longer related with this 3 in any way, and there's no data hazard. So problem 1, detecting data hazards. So let's find the data hazards in the following code. So as you can see here, we have a load word which writes into register 1. And immediately after, in add 112, we read register 1. So there's a dependency and there's a dependency. So that's going to be a problem because it's 1 instruction away. It's 0 instruction. It's the instruction immediately following the LW. And then here in add 151, we have a read of register 1 immediately after a write, or 1 instruction after a write. And that's still going to be a problem because register 1 is still not the correct value until we get to this point here. So those are going to be our 3 dependencies for register 1. And next, what we have is add 112. So you can see here that we write into register 2 here, and we do a read on the NOR. So there's going to be a dependency here. And same thing with the add 151. We have a read here, we have a write here to register 1, and we have a read below. Next, what we're going to do is we're going to learn how to resolve these data hazards. So the first one we're going to cover is using avoidance. So avoidance is basically inserting no-ops into the assembly level code. And why is this good? Well, we don't have to do anything for hardware. It's all the programmer's job. And now, why is this bad? So old programs, legacy code, may not run correctly on new implementations due to a different number of pipeline stages. So the number of no-ops we insert into the assembly code is dependent on the number of stages. So if we were to double the number of stages in our LC2K pipeline data path, we might have to insert way more no-ops, and legacy code that only inserted the 2 no-ops we needed may or may not work anymore. And programs get larger as no-ops are inserted, and while the CPI approaches 1, many instructions are useless no-ops. So basically, even though the CPI is 1, we still don't have terribly great performance. So how do we avoid these data hazards with no-ops? So we're going to do the same program as above, and we're going to insert no-ops to avoid the hazards. So we have LW05 neg1, LW01 data. And then note, we had that dependency on add 112, right? So we have to insert 2 no-ops, so it's 2 instructions away. And now we have add 151. And there's no, remember that there used to be a dependency here, and also the second instruction. But since we cleared this instruction's dependency of LW01 data, add 151 is also no longer dependent on that either. And then after that, we have to insert a no-op for the 2 and the NOR. And now remember that this add was dependent on this SW, but since now we have 2 instructions in between, it's no longer dependent. So we do not have to insert a no-op. So we can kind of save, we can overlap no-ops to improve performance very slightly. And then next, what we can do is we can do the same thing where we insert these no-ops, except instead of using avoidance, we can now use detect install. So detect install uses the hardware to insert no-ops for us. We store the destination register of the previous 2 instructions. Then we compare each source register to our stored values. And if we find a match, we insert no-ops in the decode stage to stop the fetch stage from advancing. So detect install is a direct upgrade because we use hardware. So one of the really good things is old programs still run properly. This is really important because, as you can imagine, there are many large companies that use very outdated hardware. And if old programs didn't work, people wouldn't buy the new CPU. They want their old programs to work. They don't really care about performance. And that also makes software people really happy because they don't have to manually address hazards themselves. This makes software people's lives very easy, and it also gives them a layer of abstraction so they don't have to worry about these data hazards. So one of the cons is performance is still low because we insert no-ops into the program. We still have to insert these. Even though we're not inserting them at the assembly level, we're now just inserting them at the hardware level. And then finally, we have our higher hardware cost. Because now we're actually adding additional hardware like this, our CPU is now more expensive to manufacture. So now for problem 3, I'm going to show a pipe trace of detect install. So in the first, for the first command, we have our IF stage, then we have our ID stage, our execute stage, our memory stage, and our write back. Now for LW01 data, since there's no dependencies, it's going to be the exact same thing. IF and write back. Now remember, this add was dependent on the 1. So that means we have to make sure when we IF, when we do our fetch, we see that it's dependent on register 1, which was one of the destination registers of the previous 2 instructions. So that means we have to stall. So that's going to be ID star, and then ID star again. And then we can continue on to the ID and execute and the memory stage and the write back. And the way this works is because at time 6, we know that register 1 now has the proper data from memory. So that means we can now perform our execute. And same thing as below. So on this add doesn't have a dependency on anything, but its IF stage starts at time 6 because we can see here we stalled the add. So IF, ID, EX, mem, write back. And then for our NOR is, the one thing to remember is our NOR was still dependent on register 2, and we didn't add any no-ops. So we have to add that, we have to stall for one stage. So we have our IF, our ID star, and then our ID, EX, mem, write back. And basically this ID star stage is a delay, basically is a stall. It's basically an no-op being inserted into the stage as opposed to an actual instruction. And then finally, we just have our IF through write back. And the answer just is what we wrote above. And another thing we can do is we can use no-ops, and we can improve on this by using detect and forward. So detect and forward feeds the output of some of our stages back into the execution stage. And when executing, if a hazard is detected, we use the correct updated value. And there's one exception. We still need to insert a no-op for LW. So how would this look? So let's assume we had the instruction add 112, or I'll write it down there actually. So let's say we have the instruction add 112, and immediately after we have nor 246. So we can see that there is a data dependency, right? But with detect and forward, what happens is we know that after the execute stage for add, register 1 plus register 1 has already been computed and is in ALU results. So we can just forward that ALU results to the NOR where it's needed, because we know that NOR has a dependency on register 2. So let's go through this example in problem 4. So we have our IF through ID, EX, and MEM, and then we end with our write back stage at time 5. Next, we have our LW, and again, there's no dependency. Now, we have our dependency on add, right? And we have to wait all the way until our write back stage before we can execute anything for our add. Because the one thing is that anything that gets forwarded is forwarded from the execute or memory stage. And what would get forwarded in the case of LW? Well, LW computes reg A plus offset. But the important thing to note about an LW is we're loading in from memory. We're not trying to get this value inside the register. We're trying to get the memory value inside of the register. So we have to wait all the way until the write back stage to resolve that. So when we do our add, we do IF, we stall for 1, and then we do our execute, mem, and write back. Oh, oops, I'm off by 1. So we have our ID star stage, stalls by 1, and then we do our true ID stage, and then we do our execute, and then mem, and then write back. So how come we had to stall for 2 before, but now we can only stall for 1 stage, even though it's an LW? So the reason why we can stall for 1 is because this write back stage can write back immediately while the execute is running. And then again, we have our IF stage for our add, and then ID, EX, mem, write back. And none of the other instructions have a dependency on an LW, so they all are just followed one after another. And then finally, we're going to talk a little bit about pipeline performance. So question 5 asks, we have 1,000 instructions in LC2K to benchmark with. 35% of these 1,000 instructions are an LW, 50% of which are followed by a dependent instruction. 30% are store words with no comment. 25% are adds, with 50% of them followed by a dependent instruction with a non-dependent instruction in between them. And so that's going to look like add, no op, and then add dependent. And then 10% of these are NORs. So let's assume that we fix the code by inserting NOPs. What is a CPI? So first, we have to figure out how many dependent instructions we add. So we have 35% of our instructions are LWs. And 50% of these immediate instructions are followed by, we remember from the above that 50% are followed immediately by a dependent instruction. So that means we need to insert 2 no-ops. So that means we have 0.35 times 1,000. So 350 times 2. So that means for the LWs, we have to insert 700. So we insert 700 no-ops for the LW command. Oh, sorry. So I actually did the math wrong. So 0.35 times 0.5 times 1,000 times 2 is equal to 350 no-ops. Next, we have the 0.25% adds, 50% of which are followed by a dependent instruction with a non-independent dependent instruction between. So 0.25 times 0.5 times 1,000 times 1 for the 1 no-op we insert. So that's equal to 125. And then we just add these two numbers up to get the total number of no-ops. So that means we have 1,000 lines of code plus 475 no-ops. And so remember the way we calculate the CPI for pipeline, we also have to add that 4 to fire up our pipeline processor. So that means our CPI is calculated as follows. And then how many instructions do we execute? Well, so all these 475 no-ops were actual instructions added to the assembly code. So it's 1,000 plus 475. And I'm going to write that out a little neater. So we have 1,000 for instructions plus 475 no-ops inserted, and then plus 4 to fire up our pipeline register, our pipeline. And then we also have 1,475 instructions total to execute. So that means our CPI is 1.003. So this looks like a pretty good CPI. However, the one issue is about half of the instructions we ran, or 1/3 of the instructions we ran, were no-ops. So low CPI does not imply high performance. Next, we're going to use detect install to deal with the hazards. So what is the CPI? So above, we know that we inserted 475 no-ops, right? So that means the number of cycles we have is 1,000 plus 475 plus 4. However, this time, the number of instructions we ran is only 1,000 because we inserted these no-ops as stalls in the hardware, not as actual instructions. So that means our computation is 1,479 over 1,000. So it's the same number of cycles, but since we ran fewer instructions, our CPI goes up. Even though so yeah. And then finally, we're gonna find the performance with detect. So this is the performance of detect install. We're gonna find the performance with detect and forward. So the only number of no-ops you need to insert this time are the 175 no-ops for the LW. And so the way we do this computation is 1,000 cycles for instructions, 175 no-ops inserted, or 175 stalls, plus or 4, and then over 1,000. And we can see that this CPI is lowest, so this is probably the best performance. But as above from part A, we can't usually use CPI to make a judgment call about how fast the processor is going to go. All right, so that's the end of the discussion. I hope you learned a lot, and if you guys have any further questions, just post them to Piazza.